Start. Let me introduce our speaker today first. Welcome everyone to our today's ASP seminar. Today's we are happy to have Siyan Zhao, third year PhD student from University of California, Los Angeles, to talk about D1 scaling reasoning in diffusion large language models via reinforcement learning. Siyan's research focuses on scaling reasoning capabilities in large language models and aligning them with human preference. Recently, she showed a strong interest in diffusion-based large language model. Let's welcome Sian for today's talk.
Yeah, thank you, Xinyu, for the introduction. Should I share my screen now?
Yeah, I think you can share it.
Okay.
Yeah,
Can
yeah,
you see my screen?
yeah, we can see it. Yeah, it works.
Yeah, hi everyone. I'm Siyan Zhao and happy to be here presenting our recent work on scaling reasoning in diffusion large language models via reinforcement learning. And this is a joint work with Devansh, Qin, and my advisor Aditya. So yeah, our work is motivated by that. Like recently, we have seen that autoregressive LLMs have benefited a lot from RL post training. For example, DeepSeek R1, Kimi K1.5. RL has enabled these LLMs to generate and explore themselves with reward signals rather than SFT on static dataset. And the R1 has also found that if just apply RL on the base model, it can incentivize or elicit sophisticated reasoning traces from these LLMs. But however, these advances have primarily been limited to these autoregressive LLMs, which generates tokens from left to right and in a sequential manner. But in parallel, recently, diffusion large language models, or DLMs, have emerged as promising alternatives to these autoregressive language models. For example, in February, the LADA AB has been open sourced. It is the first DLM that is trained from scratch and scaled to 8 billion parameters, and it has a competitive or even better performance than the similar sized Llama 3 AB. And similarly, recently, Dream 7B is also open sourced, which is a diffusion reasoning model that has a better performance than prior DOM and the similar sized AR models in a lot of reasoning tasks. And these DOMs like LADA and the Dream generate through an iterative denoising process, which is they will initialize from a random noise or just purely mask tokens, and then it will gradually denoise at each step. It will unmask some tokens, and in the end, it will be fully unmasked to a full sequence. So here is a generation example of Dream 7B instruct. Yeah, compared to autoregressive LLMs, DLM has the benefits, including that it can do parallel decoding, in the sense that it can unmask multiple tokens at each step. Compared to AR model can only generate token by token, in default. So this means DLM can have potential for more efficient inference. And secondly, DOMs can employ bidirectional attention mask, which helps mitigate the reversal curse that has been found in AR LMs. And in this table, we have seen that the Dream 7B and LADA AB are the DLMs we introduced, and it has only gone through SFT training recipe. As compared to the similar size AR model, they have gone through the SFT plus RO. So we have noticed a gap that no RO post-training has been applied to DOMs. And in this work, our goal is to bring RO-based reasoning improvements to DOMs. To give background on diffusion language models, it can primarily be categorized into two categories. The first one is mask diffusion language models. where we will add a mask token into the vocabulary, and then the noising process is randomly replace the actual tokens with this mask token. For example, set absorb uses the absorbing state transition matrix. It is a mask DOM. And this is similar to BERT's mask language modeling approach. And the second category is uniform diffusion language models. The difference is that instead of replacing the actual text token with the mask token, the text token can transition to any other token in the vocabulary with uniform probability. For example, set can also adopt this uniform formulation. And prior work have found that mask DOMs are generally better than the uniform DOMs, and it scales better. For example, we have introduced LADA and Dream, and also Diffusion Llama. These DOMs that scales larger than 7 billion are all based on mask DOMs. So in this work, we will focus on applying policy gradient reinforcement learning to mask DOMs. And we have mentioned that mask DOM uses this mask modeling approach that is similar to BERT model. So both models have this mask token, and then they are all trained with cross entropy loss. The difference is BERT has a fixed masking schedule, not schedule, it just has a fixed masking rate. For example, around 15% of the tokens are masked. But for masked DOMs, it has a very masking rate that changes over time. And this makes the masked DOM a principled generative models. And in inference, BERT can do infilling task in a single step forward pass, where it can predict all the mask tokens in one forward pass. But for mask DOMs, it will do multi-step iterative denoising over many diffusion steps to iteratively unmask text tokens. And mask diffusion language models forward pass, it will corrupt the actual text token sequences with mask over time t from 0 to 1. At any time t, each token will remain unmasked with probability alpha t. And alpha t is the design choice, which is the noise schedule, and it strictly decreases as t increases. When t equals to 1, all the tokens in the sequence are masked. To train a mask DOM, for example, LADA employs the noise schedule alpha t equals 1 minus t, and it also need to initialize a unmasking predictor neural network, which employs bidirectional attention mask, and the LADA initializes with a transformer. During training, it will sample a t from 0 to 1, not including 1, and it will mask the tokens in the sequence with that alpha t. And then the task is to predict the mask tokens' original tokens, and it is trained with this cross entropy loss. This indicator means that only the tokens that are masked is used for calculating the cross entropy loss. And there is another approach to train a large mask DOMs, which is adapting from existing strong autoregressive models. For example, Diffusion Llama adopts from Llama 2.7b, and Dream adopts from Q1 2.57b. And in their adaptation, they have changed the prediction manner, where they will predict the mask token in a shifted manner. For example, in this figure, this is the diffusion modeling in the Dream model. This token will predict its next token is, and this will allow for like less OOD task for the weight initialization from existing AR models. And then in Diffusion Llama, it also has this gradually annealing the AR's causal attention mask to a bidirectional mask during training. And in the end, it can operate with the bidirectional mask. And going back to Lada scales up max DLM from scratch to 8 billion parameters. And here are the training diagrams and also its inference diagrams. In the left, during pre-training, it will start with sample of text sequence and then sample a mask ratio T. And then according to alpha T, it will mask the tokens. And then the neural network mask predictor will predict the original token for these mask tokens. And then in SFT, the difference is that only the response tokens are masked, and the mask predictor are also tasked to unmask these mask tokens. And then at sampling, Lada has this I guess limitation is that it will have predefined response length. So for example, given a prompt, it will initialize a predefined sequence of response tokens as all mask tokens. And then in each denoising step, it will take in this sequence or partially unmasked sequence to the mask predictor. And the mask predictor will predict for all the mask tokens. And then it will decide which tokens to actually unmask and which tokens to remask. So here it has decided that these two tokens to unmask and then the green box to remask again. And then finally, after iterative denoising step, it will denoise to the fully unmasked sequence. And Lada also finds that instead of randomly choosing tokens to unmask, uh, they use a approach called semi-AR decoding, where they decode in a block-wise manner. So here it has divided the response sequence into 3 blocks, and only after the block 0's mask tokens are fully unmasked, it will proceed to next block to unmask the next block. And then one thing to note that when it is predicting for block 0, the model actually does bidirectional attention to all the future blocks. But I think this kind of implicitly give it a sense of how long the response sequence length should be for it to plan the actual generation traces.
And how is the end of string token dealt with here?
Can you repeat the question?
How is the end of string token represented or predicted?
Yeah, so if it decides to, for example, end here, it will unmask a EOS token here, and then in
Mm-hmm.
the end, in block 2, all the block 2 will be Lada will predict padding tokens for block.
I see. I see. I see. Thank you.
Yeah. Yeah, I guess the detail is Lada can decide what's the actual effective tokens to predict by predicting the EOS token in advance to the actual initialized response sequence. Yeah, and proceed to the background for policy gradient methods for post-training LLMs. Currently, like I think PPO are the dominant method for post-training LLMs, and it requires explicitly training a state value function to estimate the advantages, which brings high compute and memory cost. Recently, DeepSeek R1 has found that the group relative preference optimization, or GRPO, can also scale pretty well, and it avoids learning a value model explicitly, but it calculates the advantage through group statistics. So for each query, it will sample G responses from the old policy, and then it will calculate advantage for all the tokens in the response using this normalized advantage. So you can think of Ri as the state action Q value, and then the mean of the reward in a group as the G sample size Monte Carlo estimate of the value function of the state, which is the state of the query. The state is the query. And then it will divide by the standard deviation of the reward in the group. And in our implementation, we actually remove the standard deviation as we think that adding this will cause bias, and it is not the a true estimator of the A. And this brings the GRPO objective. In this equation, it has adopted the clipped ratio as well as the KO penalty, which constrains it from deviating too far from the prior policy. And looking at the GRPO objective, we find that to calculating this loss, we need to compute the log likelihood ratio of pi theta and pi theta odd at both the token level, which are multiplied with the advantage weights, as well as the sequence level, which is for the KO term. And this is very easy to compute for AR model, since AR LLMs directly trained with next token prediction. It is modeling the exact per token log probability with a cross entropy loss. And through chain rule of probability, it can efficiently calculate the per token log prob within one forward pass. But however, DOMs does not adhere to this sequential factorization, as it is trained to maximize the variational lower bound, and to actually compute the exact marginal likelihood for DOM is actually intractable. So for DOM, we use an approximation for the sequence log probability through mean field approximation. Since DOM treat the token sequence as a whole and its sequence level log prob does not have the AR decomposition, we used a simple mean field decomposition that approximates the log prob of the completion token, the completion sequence O by the sum of the log prob of each token OK in the completion O. The main idea of mean field approximation is it will approximate this complicated joint distribution over these many variables with a product of simpler independent distribution, which is essentially treating each token in the O as independent. And next, we also have an estimator for per token log probability. The per token log probability is also inefficient to compute through DON because each token is generated like in the denoising process, which needs us to invoke the unmasking predictor, the neural network, multiple times to actually unmasking all the tokens in the completion. So to efficiently estimate it, we use this one-step estimator where we create an input to the predictor is that for a prompt Q, we will perturb it by randomly adding mask to it, and then we append a mask sequence of length of that completion, and then we concatenate this sequence and as input to the unmasking predictor F theta, and then through one single forward pass, we get the log probability estimation of each token with this neural network input. I guess an illustration of what I have described is in this figure. On the left is the mask DOM generation diagram where we have a prompt and then we initialize the mask sequence with predefined length, and then through iteratively denoising, it will unmask to a completion sequence, and then this one-step log probability estimation will first it will apply random mask to the prompt Q, which is first row, and the second row is a fully masked sequence of length of the completion, and then we send this to the neural network, and it will give logits for each position in the completion, and then we use this to get the per token log prop for the completion we have obtained earlier. And to contrast with MC type of approximation of log probability is that, so for example, here is an algorithm Lada used to approximate the log likelihood of the response. So here the notation is they use p theta to denote the mask predictor and the prompt p0, and it has obtained a response r0, and it has the defined number of Monte Carlo estimation step NMC, and their goal is to get the log likelihood of the response R0. And the way they do it is they have a for loop for the Monte Carlo estimation steps. And then in each step, it will randomly sample tokens from R0 to mask. And then they calculate the log likelihood to accumulate the logits that is assigned to the response token, which are masked in the model input. So in this MC estimate, it will randomly sample token to mask from the response and collect the log prop, and then they will accumulate to the log likelihood, and then finally they will get the log likelihood of the response. And they have found that in this approach, the MC sample size NMC 128 can stabilize the estimation. But however, if we use this MC type of approximation for online RO, this will be very expensive because in the loss objective, we need this log likelihood to and backpropagate through the computation of the log likelihood, and this will create a massive computation graph with hundreds of forward passes and creating excessive memory usage. And in contrast, our work uses a one-step log probability estimation where the model only needs to do one forward pass, and we get the per token log prop in this forward pass, and then we use this to optimize the GRPO objective. Yeah, so I think in here, one may ask a question is, why do we apply random masking to the prompt? We can get the log probability of the completion token by just appending the exact prompt queue. So the reason for adding this is as follow. So in the GRPO in the original GRPO algorithm, or this GRPO iteration. Also, in this red box, it has the inner GRPO iteration, which means that for a batch where we sample the generations for the prompts, we can reuse the generations multiple times for gradient updates instead of discarding them after a single gradient update. Since the bottlenecks of this online RO method is generation time. So this is the key to make GRPO more sample efficient to reuse these generated samples during optimization. And this has been introduced a long time ago with PPO. So here is the.
Sorry, can you repeat why this is then the reason for the random masking of the prompt?
Yeah, I think, yeah, I will get to that point later.
Okay.
After introducing this.
Okay. So.
Yeah, no worries. Yeah, so in the in practice, so you can see here the GRPO iteration can scale to 1 to mu, but in practice the mu cannot be very large. If it's very large, it will impact the learning, as the inner iteration is kind of doing off-policy optimization, and it will cause issues in learning and likely due to off-policy optimization as well as overfitting. For example, in this graph, this is obtained from the OpenR1 update from Hugging Face TRL library. They have experimented with Q1 2.5, and here the number is the mu, and they have found that so in here the lower curve are mu equals to 1 or 2, and then the upper darker curves are mu equals 4, and then this lower black curve is mu equals to 8. So they have found that if increase mu to 4, it can greatly improve the learning efficiency. As you can see, the x-axis is the word clock time, and with the to achieve the same reward, with mu equals 4, it can do this within 1/3 of the training time. But they suggested that mu to be the best mu to be 2 or 4. But because you can see when mu equals to 8, the performance actually drops. Yeah, so this is a problem of scaling mu to be very large for this inner policy gradient optimization iterations. And to go back to why do we use random masking for the prompt? So here you can see that on the left is iteration 1 to n, which is the GRPO policy gradient iterations. And we apply random masking to the prompt in each iteration. This sequence will be sent to the neural network, and it will predict the per token law prop for the fully masked completion. So the gradient changes in the color gradient in this per token law prop means that the values are similar for this per token law prop, but with some variation. Yeah, so the key for this is that with the same prompt and completion pair, we can create different input data to the neural network, and this will serve as some kind of regularization to avoid overfitting to the same batch of prompt and completions. And in practice, we have found that this allows us to scale mu to much larger values. For example, if you compare mu equals to 2 and mu equals 12, in the x-axis is the number of completions generated. You can think of it as a proxy for the word clock time for training. And here you can see that when mu equals 12, with the same number of generated completions, it can achieve higher rewards. And we also noticed that when mu equals 24, it will initially it will have very high learning efficiency, but later it will deviate.
Do you think it's worth also doing this in the autoregressive case as a side?
Can you repeat the question?
Do you think it's also worth doing randomly changing the prompt to when we calculate the mu in the normal GRPO in the autoregressive setting?
Yeah, I think that's actually
Because
one
of the
potential research direction. Like in AR model, we can also do some like maybe random dropout to the prompt.
right, right,
Random ask it to rewrite the prompt to a similar manner and then do this
right.
optimization.
Mm-hmm.
Yeah, we thought about this idea, and yeah, I think it's worth trying.
Yeah.
Yeah, so this finished introducing our RO algorithm diffuse GRPO, and so here we introduce our framework for scale DOM's reasoning, which we name it D1. So it has two stages. In the first stage, we will do SFT on a high quality reasoning dataset. The goal is to instill reasoning behaviors. And then in the second stage, we apply our diffuse GRPO algorithm on the SFT model to further reinforcing or extracting out the good reasoning traces. And we instantiate D1 using the LADA AB instruct as our base model. In the first stage, we apply mask SFT on the S1K dataset. So S1K dataset has 100 high-quality reasoning traces, and it has detailed step-by-step reasoning traces from Gemini thinking models, which includes verification and backtracking mechanism. And we do masked SFT on this dataset, which is the same algorithm as LADA, where we only apply masking to the response, and the mask predictor will be tasked to predict the original tokens. And in the second stage, we do diffuse GRPO on 4 reasoning tasks. And we know that we train on these 4 tasks individually. So we have a JSON AK Math 500, countdown, and the Sudoku puzzle task. And the reward function for these tasks are generally we use rule-based reward for correctness and also for formats. Here are the results. So this result is a qualitative result from applying SFT on S1K dataset, where we noticed that after SFT, it has exhibited the expected self-correction and the backtracking behaviors, where in the blue sentence, it starts to question its previous answer and it generates a new reasoning traces. And here is a main result we have in comparing different training recipes. So we know that since LADA in generation, it will need a predefined generation sequence length. That's why we evaluate each task with a different sequence length from 128 to 512. And here, the first row is the LADA AB instruct, the baseline model. And then the second row is we apply SFT on S1K on the base model. And it has some improvements, but not consistently. And the third row is we apply diffuse GRPO on the baseline model. We can see that it has a consistent improvements over the base model and over the SFT model. And then
And
the
this is, sorry, and this is with mu with a very high mu, right?
yeah,
Yeah.
I believe we do mu equals to 8 or 12
I see.
with the diffuse GRPO. Yeah. So we have found that diffuse GRPO consistently outperforms both the LADA baseline and the SFT model. And also we found that with diffuse GRPO, it can outperform its initialization checkpoint, which means that in the fourth row, we apply diffuse GRPO on top of the SFT model. It can also gain improvements over the third row. And we call the fourth row the D1 recipe, which is doing RO on top of SFT, and this D1 recipe yields the highest gain. And we want to know that when we apply diffuse GRPO on the model, we use a fixed length generation, which means that in the GRPO sampling, all the response lengths are initialized to be 256. But we noticed that even when generation has fixed length, it can generalize beyond this training sequence length. It has improvements over other sequence lengths at 128 and 512. Yeah, and compared to other SOTA DOMs and other similar size ARLMs, we find that D1 LADA has on JSON AK, it achieves the highest performance. In the brackets, it means how many few shot examples are given, and our model does not use few shot example. And on math, D1 LADA has a better performance than prior DOMs and slightly worse than the AR model. the Q1 2.5. We also examine what's the effective tokens after training the LADA model. We define effective tokens as the number of non-padding and non-EOS tokens in the response sequence. So as I mentioned, the LADA can early terminate its generation by outputting EOS tokens in advance and then generate padding tokens later on. So we calculate the number of tokens that are actually the actual effective tokens before the EOS. And as expected, when we initialize the sequence length from 128 and 512, it will increase the effective tokens number. But we found that, for example, in GSM-AK, when sequence length is 512, the actual effective tokens terminates earlier, around 300, so which leaves the remaining 200 tokens as padding tokens, which I think is the inefficiency of this kind of generation. And additionally, when we're looking at how each training method affects the effective token, if you look at GSM-AK, we have found that diffuse GRPO, applying diffuse GRPO alone on the LADA model has decreased the effective tokens very obviously. And then SFT model, which is the purple bar, has slightly increases the effective token. But then if we apply RO on top of the SFT model, which is the dark blue bar, it can further increase the effective token. But this, I guess this trend is not like general in another task like Math 500. But we still notice SFT increases the effective token, and then diffuse GRPO has less effective token than SFT, and then applying RO on top of SFT. We also conduct ablation on the masking rate on the prompt. So earlier we have said that we apply random masking to the prompt. So this random masking is applied according to a masking probability. So here, this ablation is on applying ablating the masking probability from 0.1 to 0.7. I think this is a very expected ablation because if we mask a lot of prompt tokens, then the performance will decrease. I think an improvement to this prompt masking method is since there are some tokens in the prompt that are very important for solving that problem, so we want to keep those tokens not masked in computing the per token log prop. Yeah, so to for the limitation and the future work directions, we first acknowledge that in our diffuse GRPO training, we use a fixed length generation because LADA requires predefined output length. I think this will limit the model's ability to discover what's the optimal reasoning paths. For example, in DeepSeek R1, they have found that when they train GRPO, the reasoning length increases. I think in here, when we train with fixed output length, this might hinder the emergence of some advanced reasoning strategies. So one future direction is to apply diffuse GRPO on block diffusion, which has a variable length generation to enable more flexible length generation in RO online sampling. And this another limitation of our work is we train our model on each task individually. So one future improvement is we want to train a single DLM on our large reasoning dataset with our diffuse GRPO algorithm. And we also found some practical limitation of SFT on LADA is that LADA needs to take loss on the padding tokens because it needs to effectively terminate its generation by outputting EOS and then outputting padding token after that. And in Lada's SFT training, it passed to the longest sequence in the batch. So which means that in different batch size, the padding to the longest sequence is different. So this will affect the training performance. So we found that because in our setting we have less GPU memory, so we can only do batch size of 1 or 2. So in one of our experiment, we found that we do not do any padding with batch size equals 1. This kind of breaks the Lada's performance a lot. And another limitation is when we first started training Lada on S1K, S1K has a lot of traces larger than 496, but Lada has a sequence length limit of 496, so we train on a lot of truncated sequence. And then after this, we found that Lada starts to generate a lot of unfinished response, which is also a disadvantage. So I think another future direction is to improve the SFT robustness of training on this Lada DOM. Yeah, I think this concludes my talk. And we have also open sourced our code, and here are the links to our paper and the website. Yeah, thank you for listening. If you have any questions.
I think there's one questions in the chat. Yeah, it's asked why S fine-tuning seems to hurt Sudoku performance.
Let me see. Yeah, I think it has some increase in 2 of the setup and decreases in some setup. Yeah, I think qualitatively, when we're looking at the generations, we find that even when given SFT on the S1K dataset will give the DLM the ability to do self-tracking, back verification, no self-verification and backtracking. But we found that it sometimes can override its previous correct answer to a wrong answer. So I think that with longer sequence length, like 512, it may do this, and then this may cause some performance drop. And as well, like for countdown 256, we also noticed a performance drop. Yeah, I think as I mentioned in the last limitation slide, the mask SFT currently on Lada is not very stable, and we train with a small batch size. I think it's very different than what Lada SFT's batch size is. So I think that may cause some performance drop.
In the SFT with the pads, can the pad tokens, their loss be weighted down somehow for the pad tokens so that the number of them don't affect the final loss?
Yeah, so let me think. Oh, you mean the loss on the padding token can weight down?
Mm-hmm. Yes.
Yeah, but I'm not sure if it will let me think, break the loss function. And it may
Right.
need the padding tokens to determine when it will early terminate the generations.
Right. Just yeah, just a thought.
Yeah.
Yeah, I think I also have one question is about because that you mentioned that you do smart fine-tuning first with reading data on the S1K data, and I was wondering that because that it seems that you need to random masking the tokens, how we can mimic the real generation process. For example, maybe easy tokens generate first and then hard token generate later, or you just do it randomly.
Oh, you mean in the decoding process?
Yeah, yeah. Or maybe in the training process, yeah, just how to maybe teach the model first decoding the easy token and next the hard tokens because that if you do it in a reverse way, I don't think it should be a very good training signal.
Yeah, I think right now it's doing training is like randomly choosing tokens to mask, so it does not have a sense of first it will unmask easy token and next unmask hard tokens. But I think that is actually a direction that we were exploring before. Like in training we have a we kind of weight the tokens by how the loss, like the model's loss on them, and then we choose the highest loss to, um, predict later, and then the lower loss to predict first. So I think it's similar to your idea to like learn to predict the easier token first, and then the harder tokens, next. But yeah, I think we do that experiment on the GSM-AK dataset, and we found that it will first predict the in the response it will first predict the like equation signs like plus minus, and then later it will predict the uh value numbers in generation. Yeah, I think that's actually a doable research direction, but we haven't done like comprehensive experiments on them yet.
Yeah, thank you very much. And it seems that why you trained maybe for 20 epochs because that I think that for the original S1 they only maybe trained for super and tuning they only trained for example 5 exact epochs. Yeah, and they use much longer sequence length. Yeah, would it will result in some issues that because that I guess that the recent trains are much larger than much longer than the 4096. Yeah, I guess you need to truncate them.
Yeah, I think my intuition is DON maybe needs more epochs to learn than AR model because it is like in each sequence it is only unmasking the mask tokens, but in AR model is predicting all the tokens in the sequence for that data sample. So which means in DLN it only learns the mask tokens in that example. So I think that explains why it needs more epochs to learn for the than the AR models.
Yeah, thank you very much. Yeah. Uh, Yeah, and do you see any different maybe behavior that of the only supervised fine-tuned model and model with we after use diffusion GRPO? Because that one I previously trained on the S1 model that it seems that their model cannot maybe finish their generation for maybe 50% or maybe 30% of the test cases. But I guess that the diffusion model will do better on such issues. So just I want to know that whether maybe some behavior different about the model trained with different kind of method.
See. Uh, so do you notice the like truncated generations on AR models?
Yeah, yeah, I know it. Yeah.
I see. Uh, Yeah, I think we also noticed some unfinished generation after training on truncations on S1K. But I think here in this SFT, we do not train on truncated sequences. And also, like in our prior experiments, we found that even if SFT model generates truncated sequences, the diffuse GRPO has a format reward. And also, the correctness reward depends on extracting out the final answer. So it kind of implicitly encourage it to generate a full response. Like otherwise, it won't get the reward for that generation. So I think the RO kind of mitigates this truncation generation issue.
Yeah. I think I agree with this issue. Yeah. And how you think maybe the method can further scale to more real-world reasoning tasks, such as Amy and maybe
Yeah. Yeah, I think one bottleneck is the online sampling speed. I think right now we're doing is we fix the generation length to 256 in online RL sampling, and we use 128 diffusion steps. I think that is still very slow. And if scale to harder problems, for example, we want the generation length to be higher. For example, 1024. Then this we we can I think better decoding methods for DLN will help scale online RL for DLN like very well. Like for generating a 1024 sequence, we don't need 512 diffusion steps. Then that will be much better to scale this RL post training for DLM to a much harder dataset and much harder reasoning task. I think one thing we are doing right now is we are training a unified RL model on LADA using open source 2 dataset, and we hope that training on that we can test on harder tasks like Amy.
I see, yeah. Because I only do some super fine tuning, and I think that if you want to do Amy with only super fine tuning, as they typically require a 32 billion AR model. Yeah.
Yeah.
But
Yeah, well, I think we also found that when we train diffuse GRPO on open source, which is of harder difficulty than like GSM AK, we find that like half of the generations have zero standard deviation of rewards, which means I think the current LADA based model is it cannot solve half of the problems in open source too. So I think that is also uh, a limitation of scaling LADA 7B to harder problems.
I see, yeah. I think also maybe the base model quality of LADA may be not good enough. Yeah.
Yeah.
I see. Yeah. Yeah. Thank you very much. Do anyone have more questions? That feel free to ask. Yeah, if there's no more questions there, I can maybe ask the last, maybe just very open questions that what do you, just because that many people are doing diffusion models and language models, what do you think will be the advantage of the diffusion models if they can achieve a similar performance with AR models? Yeah, because it seems that it's still need to simply many steps now, and it seems no huge efficiency gain on recent task now.
Yeah, I I feel the advantage I think I also listed here in prior slide is it I guess it is less constrained on in architecture. Uh, it has more flexibility to design more interesting architecture for DLMs, and it also parallel decoding because I guess right now the model ability is not good enough, so we need many diffusion steps to denoise to a good response. But I guess in the future, if there are more efficient decoding strategies, which only needs maybe like 1 to 2 or if like a much less diffusion steps, then it will be much faster than AR model decoding. Um, I guess that is one promising research direction. And also, I think AR LMs has the next token prediction drifts, as like Yan Queen once said, and the DOMs has this bidirectional attention mask which LiDAR has shown that it breaks the reversal curves as compared to I guess LiDAR AB compared to a GPT-4 level model, it achieves better performance. I think that is also promising as compared to ARLMs.
Yeah, I think there's a good point there, but I guess, yeah, because I think that some people that mentioned that the current model seems that they still need many steps. Yeah, so I guess that in practical, maybe there's still a gap in to be make it. Yeah,
Yeah.
yeah, thank you very much. Yeah, if there's no more questions, I think we can end here today. Yeah, thank you very much for sharing. Yeah, very impressive work and on time. Yeah.
Yeah, thank you. Thank you for the invitation.